Okay. So, in this particular example, we have already seen that how do we calculate means if I have the transmitted that prior probability known and then channel what it is doing that is also known to me, how do I calculate what is happening at the other end, and then whatever is happening at the other end, from that we can also start guessing what might have happened in the transmitter side. See, remember in communication it's the communication actually becomes successful if transmitter and receiver does not have any other form of communication, because the very communication you are building up just to give information from transmitter to receiver, if you already assume okay for that you need another communication, then it just goes on, right. So, basically you have to always understand that whenever we are doing communication, probably transmitter does not know what will be happening at the receiver, and receiver will also have no information about what is happening in the transmitter. Okay. So, they will not have this linked information, only they will see something which is being transmitted over the channel, they will receive that. If it is contaminated by the channel, they have no way to know what exactly has been done by the channel. Okay. So, they can only have, why we are doing all these things, because they can only have a statistical guess, nothing else. They cannot exactly know in a deterministic way what exactly has happened to my signal. Okay. So, let us try to see with that example. So, we could define this, right, p x y x I y j. This is something we can define from the information that we have already got. So, we have already told that this and these 4 we know. Okay. So, this p x y j x I y j, that is actually the joint. So, from Bayes theorem we can easily evaluate that this must be p y given x y j given x I p x x I. Okay. So, this is something I can write. Okay. This is equal to this. Why I have written with a condition on x, that is because I already know that. Okay. I have not written it with a condition on y, because that is something I do not know. Okay. So, this is something I know. We have also said how to marginalize it. Now, let us try to marginalize and get, what do I want to get? I do not want to get p x, that is already known. Okay. I want to get p y. So, I wish to get p y, let us say 1. Okay. So, what do I have to do? I have to marginalize this, that means I have to sum over x. So, I will be doing it over I p x y x I, and y j I have already told that takes a value 1. So, that should be 1. If I put 0, then I will get this done for 0. Okay. So, this is all that I will have to do. So, I can immediately write it in this format. So, I can write p y given x. Okay. So, now it should be y I. Okay. So, I will just write y I given x where, right. So, y I, and now I have to put this x I, right. So, x I can put anything. So, y I is for me it is actually 1. So, I can put y I as 1, x can be taken a value of x I. So, if I just do a sum, I have 2 possibilities, right. So, I can do it for 1 and then multiply p x 1, and I can do it for 0 p y given x. So, this should be 1 always, given 0 p x 0. So, I can write this way. Now, you can see I know all this already. Okay. So, I can actually calculate this. So, this is the beauty of it. Once I know all these things, I know how to calculate the individual probability also, which is unknown. So, I had the prior probability, I know all those conditional probability given x, that means given that what is transmitted. So, I can now calculate what is the associated probability of p y. Okay. So, I can write this as p x 1, that is probably p x 1 is q, and this is 1 minus p e, and then this is 1 minus q, and this is probably p e. Okay. So, that is how I calculate p y 1. Similarly, you can also see p y 0 can be evaluated in a similar manner. So, that should be 1 minus q into 1 minus p, you can just test this, and q into p. So, this should be the case. Okay. So, I get these two, fine. Now, I wish to calculate, which I was telling, that given y, I want to see what was x. Okay. So, my evaluation should be p x given y, okay, let us say, sorry, I wish to calculate this. This specifically means that I have received at the receiver 0, what is the probability that 1 has been transmitted. So, that means I have received an erroneous thing. Okay. Certainly, whatever was transmitted was 1 and I have now received 0. So, I am trying to evaluate this probability after receiving. Okay. So, we can just put Bayes theorem again. So, p x given y can be calculated as p y given x 0 1 p x 1 given p y 0. So, this I can do, okay. And immediately this is already known, which is actually p e, this is known, this is q, and p y 0 I have already evaluated, which is 1 minus q into 1 minus p e plus q into p e. So, I get this. Okay. So, this is the way we calculate this particular part. Okay. So, whenever we have something received, we are trying to guess what is the probability that something else was transmitted. Okay. For our case, something else is just another one. So, if we just calculate that, that must be our error probability. Okay. So, that is the probability that given I have received 1, what is the probability that I have probably received an erroneous thing, that something else was transmitted. Similarly, I can do it for given I have received 0, what is the probability that I have received probably an erroneous thing, that 1 was transmitted, I have received this. So, this must be your error at the receiver side, and you will try to minimize these things. So, all you will be doing is once you get this, now you have to see what has to be minimized. Okay. So, something which can be minimized is P E, that is the channel error. So, you will have to see how to manipulate that, so that we get overall error probability minimized. So, this is something people do often. Okay. So, given these things, now let us try to define another thing which will actually lead us towards continuous random variable definition. So, we will define something called cumulative distribution function, that is called CDF. So, what is CDF? Our CDF definition is something like this. We call it capital F. So, capital F x x. So, x is a random variable, this x is something we will talk about that. So, this is nothing but probability that this random variable takes a value less than equal to that particular thing I have defined. Okay. So, in the real axis, suppose for our that rolling of die, we have events which are 1, 2, 3, 4, 5, 6. Whenever we say that x is less than equal to 4, that happens to be a CDF up to 4. When we say x is less than equal to 5, that happens to be a CDF of parameter 5. So, you keep doing that. So, that means we will have to add all this probability till that point in the real axis. So, we will start from probability minus infinity and we will go up to that point x. So, this is that definition. Okay. So, immediately what we can say, there are few things which we can immediately say about this. F x x, can we say this? That is always true, because whatever happens, it is just a probability, and probability must be, we have already discussed that, probability must be greater than or equal to 0. So, this must be the case. Now, that is the first thing. At minus infinity, so that means this sum goes up to minus infinity, okay, and it starts at minus infinity. So, it could not take anything, any probability value. So, this must be 0. Okay. At infinity, what it should be? At infinity means I have taken all the probability. that means all possible probability values for all the random outcomes. I have already summed them, and we know that summation of all those probability must be 1. So, this is a function which starts at 0 at a minus infinity level in the real axis and goes up to plus 1. Okay. Now, let us see the nature of the function. So, we will now next prove this part, that this is always less than as long as this happens. Okay. So, we will be trying to prove this. So, this is will be with this we will be able to say that it is a monotonically increasing function. Okay. So, let us see how do we prove this. So, let us write f x x 2 as probability. By definition, x must be less than equal to x 2. This I can write as p x less than equal to x 1. So, this union x from this, I can always write that x less than equal to x 2 means that I take those x which goes up to, because I know x 2 is greater than x 1. So, I go up to x 1 and then the rest of the set I take. So, these two set I can always write, it is the probability that this union this. Now, these two set by definition they are disjoint, because whatever is covered within this is not covered within this. Okay. So, they are disjoint. So, we have already proven that probability of union of two disjoint events must be summation of probability. So, this must be probability x less than equal to x 1 plus probability that your x remains between these two. Okay. Now, what is this? By definition, this is f x x 1. This is a probability value, whatever it is, that must be always positive. So, this is always positive. So, what is happening? This particular value is some value plus some positive term. So, this must be greater than equal to this, at least this can be 0. So, I can from this definition immediately I can write f x x 2 is always greater than equal to f x x 1. For all x 2, by definition we have taken x 2 as greater than, otherwise I could not have written this, right, x 2 greater than equal to x 1. So, for all these things this must be happening. So, I can always write that this is a monotonically increasing function. Okay. It will never have a dip. So, it will never go down, it will just increase from 0 it will start, it will go up to 1. So, all these things we have proven. So, this particular function some characterization we have got now. Okay. Now, let us try to define something which will take us towards the continuous part. Okay. So, let us say now I have a random variable which is continuous. What do I mean by that? Let us give an example. So, we have already given an example in one of our earlier class. We have told, suppose I have a pivoted rod and just I exert a random force to it, and it starts freely rotating around the point where it is pivoted. Okay. And then it will stop somewhere. It completely, where it will stop, it completely depends on what kind of force I insert. Okay. And the amount of force that I can give, that is a continuous, any force I can give. Okay. So, accordingly he can stop between that 0 and 2 pi. So, it is a pivoted rod which is getting rotated and stopping somewhere at theta. So, this theta which is a random variable now, where it will stop. So, that can be anywhere between 0 to 2 pi and it can take any value. So, this random variable theta, now it is not taking a discrete value, it can take any value between 0 to 2 pi, any value you can think of, or any real number you can think of between 0 to 2 pi, it can take that. So, this is a typical example of a random variable which is continuous. Okay. So, that means if I just try to similarly map it to real axis between 0 to 2 pi, now it can take any value. Okay. So, the definition of PMF we have defined, that is not valid over here. Let us try to see can we give some other definition over here. Okay. So, let us say that I have this random variable which is taking a value between x and x plus delta x. Okay. So, from that previous proof, let us take x as x1 and this x plus delta x as x2. I can immediately write this as, just do not give this equality probably. Okay. So, this I can write as f x x plus delta x minus f x x. Is this all right? Because we have started defining it with f x x2, this is my x2 is equal to, we have already proven that should be f x x1 plus this probability that it lies between x1 and x2. Okay. So, this particular probability value that it lies excluding of x from x to x plus del x, that it is lying on that interval, that probability is defined by this. Okay. So, now what I do, we actually divide this by del x. Okay. So, I can or this side you can divide this f x x plus del x minus f x x, divide this by del x and take a limit del x tends to 0. What do I get? I will be getting, this is differentiation of this f x according to the basic definition of differentiation. Okay. So, eventually what I have done is I have divided this part by del x and then try to evaluate this. So, if this is that probability, this was just the separation. Okay. So, if I just try to relate this to this, I can always write that probably this part multiplied by del x and taking del x tends to 0, right. So, this particular part whatever it is, okay. So, that must be this part, right. Now, all we have done is just divided by del x and taken limit del x tends to 0. Define this as some p x x, we are just defining it. Okay. So, this divided by del x, we are just defining this as p x x. So, I immediately get p x x to be differentiation of this one, right, that definition we get. And in that process I was more interested towards this probability. So, what that is, I can immediately see this p x x, if I multiply with del x and take the limit that del x tends to 0, that must be my this p x, that is the probability. So, what is eventually happening? Suppose I have a particular probability mapping on the real axis and I have said this is my x and this is my x plus del x, okay. And I am trying to find out this particular part, which is a probability that it will be lying between this and this. So, that overall probability I am trying to report. As del x goes towards 0, what will happen? The variation of that, okay, will become vanishing, there will be no variation. Okay. So, at that point I can say safely that it is actually whatever that p x x, if I just plot it over x, and it is the area under that part which defines my probability that it will lie between x and x plus del x. So, this probability is nothing but whatever this particular thing I have got by differentiation of this CDF, cumulative distribution function. If I multiply that with a del x, that almost means as del x tends to 0. So, this p x x will not be varying, this will be almost constant. So, that multiplied by del x is almost getting the area under that curve. Okay. So, which is the definition? Now, we still have not defined what this Pxx is, but we can now see that there is a particular function Pxx whenever we take it to the continuous domain. This is just a differentiation of the CDF, if CDF is defined the way we have defined it, that it is less than something. Okay. So, that can be defined. So, that probability, that CDF, if I differentiate it, I get whatever value I get if I plot it with respect to x. So, if I just plot it with respect to x and then choose a particular x, and if I get the area under it for a very small del x, that must give me the probability that it is lying between x and x plus del x. Okay. Right. So, that is the probability that it will be. Now, what do I get from there? Suppose let us say del x goes towards 0. So, this will be almost coming to this point. So, almost I am going back to a probability of a value, okay, of a random value, like our means discrete random variable. What will be that value irrespective of Pxx? If Pxx is bounded, we know that Pxx must be bounded. As long as that is happening, what do we get? Pxx into del x tends towards 0. So, I get a individual probability 0. So, in a continuous variable like that example that I give a random force and it just keeps rotating and fix at a particular theta. Okay. So, from the very definition, frequency definition or favorable cases, let us try to think about this, that it will be stopping exactly at theta equal to 60 degree. What do I get about the associated probability? How many favorable outcomes are there? Only one, that is the 60 degree. Okay. How many overall possible outcomes are there? How many angles I can get? Infinite. So, what is my probability? It should be 1 by infinity. So, that must be 0. So, individual angles I must get a probability value of 0. So, remember that is why we taken an example of this particular thing, knowing that many of you might be knowing probability theory, and given the similar explanation for Fourier series to Fourier transform. The same thing we are doing or dealing with again. It is PMF or discrete random variable, and we will be calling that as PDF, and remember we will not be calling that deliberately as distribution function, that should be a density function. It's whenever we say PDF, it is actually probability density function, not distribution. It has nothing to do with distribution. Distribution is not that Pxx. Distribution is multiplied by this and then limit del x tends to 0. So, this is actually the probability that gives me probability, but Pxx does not give me probability. It just gives me almost like a density, that as if at that point, if I now multiply with del x, sufficiently del x small so that this does not get changed, and then I will be getting the area will be defining the probability. Okay. So, as if the probability divided by this del x gives me this, okay, as long as del x is sufficiently small. So, that is why it is becoming density, that per unit on that real axis, per unit that random variable change, what is the probability. So, that is why it is density, it is not probability. So, individually at a particular point the probability will be always 0, but there will be a relative nature of this, and that tells you where exactly the probability values are higher and where exactly the probability values are lower. So, suppose I have just drawn a PDF like this, then I will be able to say that around 0 it has a higher probability. I will not be able to say specifically that at 0 this is the probability, that will be 0, at 1 this is the probability, that will be all 0. But I can say around 0 this is the probability, and this is having higher probability around 0, whereas as I go away from 0 it will have lower probability. So, from the nature of this curve I will be always getting that hint. Okay. So, that is one thing. And the second thing that I wanted to discuss is something like this. I can always write P of suppose not this. So, this particular part we have already seen, that can be written as f x x 2 minus f x x 1. This is something we have already proven. So, what is this? This I can write from minus infinity to plus x 2. This f x x 2, we have already shown that derivative of f x x is equal to the PDF. Therefore, from the relationship of derivative and integration, we can say f x x is just the integration of p x x. So, I can write that probability distribution function going up to x 2 must be interrelated this way, minus, similarly I can write, right. So, very nicely, because I have this definition. So, f x x d dx was p x x. Therefore, from the conjugate definition of differentiation and integration, I can always write this. Okay. So, I will be able to write f x x must be integration minus infinity to x p x suppose t dt, right. So, this is something I can write. So, here also I can write that way. Okay. Immediately from this I can write it from x 1 to x 2, again from the definition of integration with respect to limit, I can write this. So, what it says that if I target instead of a single value a particular zone on that random axis or real axis where the random variable is defined, I can always integrate that PDF from that particular value to whatever value I wish to evaluate it. So, I will be getting the corresponding probability. So, if you just think about that pivoted rod, if I just say instead of specifying a 60-degree angle, I say between 0 to 60 degree it will be lying, what is the probability, associated probability. So, then there is a ratio between 0 to 60 degree is a solid 60-degree angle, and what is the overall angle, that is 360 degree. So, 60 degree divided by 360 degree should be my probability, which is 1 by 6. Okay. So, whenever we talk about a range, because it is density, I integrate it and I get a probability associated with a range, but individual value will be all 0. And that is why we were talking about this thing, right. So, in this range if you integrate, the value will be higher, associated probability will be higher, and if you integrate in this range, even if the ranges are same, probability the integrated value will be smaller and the associated probability will be smaller. So, you can always say I have more likelihood to get this random variable, whereas I have less likelihood towards getting this random variable that has lower probability. So, PDF actually tells you that information, okay, or gives you that information, and this is how they are linked. So, we will be always able to evaluate whenever we need to evaluate that it is the probability between this to this, we will be able to calculate that. Okay. So, with this definition probably we have now gone into the definition of continuous random variable and its associated functions like CDF. Remember, CDF is still called cumulative distribution function, because that is still a distribution up to x 1, what is the overall probability, that is still a probability, whereas PDF that is not probability, that is a density. So, often people do this mistake, even in Fourier series and transform also same thing happens. Whenever you go to transform, it is spectral density, remember that, whenever you are talking about Fourier series, in each frequency you will be getting a particular amplitude value or overall energy value or power value, I should say. Okay. So, there is a definite power value, whereas for Fourier transform you do not have a power value, it is spectral density actually. And there also you have seen that it is almost similar concept. You have, if you integrate from some particular value to some particular value, you get, instead of probability there, you get some amount of power or energy. Okay. So, with this definition we will stop today, and then what we will do next is try to see some more things which will actually get us toward random process. So, some more things on probability theory. Thank you.